All right, this is video number 3 as we compare what happens when we react acids and bases together. In the first two videos, or first several videos, we looked at strong acid, strong base, which was relatively easy, limited reagent problem. Then we looked at a strong base titrated with a weak acid. Titration is merely the act of neutralizing or reacting an acid and a base together, but carefully measuring molarities and quantities so that we know exactly how many moles it takes. All right, so here we're going to look at strong acid and weak base. And we'll, like before, we're going to look at about 6 different points at the beginning, before the half equivalence, at the half equivalence, past the half equivalence, at the equivalence, and past the equivalence. And I think that we can get through this in one video because it's going to be remarkably the same as what we did, only it's going to be, instead of a strong base and a weak acid, it's going to be a strong acid and a weak base. So it's going to look familiar to us. Okay, so let's take a look here. Before any acid is added, we have ammonia, which is a weak base. It ionizes in an aqueous solution according to this equation. NH3 plus water reacts to form in an equilibrium manner NH4 plus and OH minus. Kb is given as 1.8 times 10 to the minus 5th, and we're asked to calculate the pH of a 0.2 molar solution. So initially, we start off with 0.2 molar NH3, 0 NH4, and 0 OH minus. Okay, we don't know how much is going to react, so minus X on the left side and plus X on the right. So we've got our equilibrium amounts. We write our our equilibrium reaction, our equilibrium equation. And because Kb is at least an order of magnitude smaller than what we had when we had the acid problem, I feel fairly confident that we can make this simplifying assumption, which is X less than 0.005. When we do that, it's negligible compared to 0.2. We very easily solve for X, and we get X, which is the OH minus concentration, is 0.001897. So our assumption is valid. And so now we can take the POH, which is just the negative logarithm of that number, 2.72, but pH is going to be 14 minus that number, or 11.28. This makes sense. We have a weak base, but it's a base, so our pH is going to be significantly higher than 7. All right, so now we get to somewhere before the half equivalence point. We're going to add 20 milliliters of 0.2 molar nitric acid, HNO3, and we see that now our total volume is 70 mils, or 0.07 liters. So we multiply our 50 milliliters times our 0.2 molar NH3, we get 0.01 moles. We do the same for our acid, we get 0.004 moles, and we can see that the limiting reagent here is our H3O plus, so we're going to use it all, and so we end up with 0.006 moles of NH3. We divide that by our 70 milliliters, and we get our 2 molar concentrations. We write our Kb equation. In this case, we know NH4, and we are NH4 plus, and we know NH3. What we don't know is OH minus. So we can solve for that. Pretty straightforward. We get OH minus is 2.7 times 10 to the minus 5th. And as before, we solve for our pH, and now we get 9.43. We see that our pH is starting to come down, which makes sense. We're adding acid. All right, we go to our half equivalence point. Remember, the half equivalence point is when we're halfway to the equivalence point. So now we have 0.005 moles of H3O plus. We subtract those 0.005 from both sides, and we get 0.005 of NH3, 0.005 of NH4 plus, and we divide by the total volume, which is now 75 milliliters. And we can see that when we plug this into the Kb equation, both terms in numerator and denominator cancel. So OH minus is just 1.8 times 10 to the minus fifth, which is the value of Kb. And so our POH is 14 plus the logarithm of our H3O plus, which is 9.26. So here, the half equivalence point, when we have a strong acid and a weak base, the half equivalence point is when half of the base is consumed. So now the POH would be equal to PKB. When it was the other way around, when we had a strong base and a weak acid, pH was equal to pKa. So now POH is equal to pKb at the halfway point. Okay, we go past the halfway point. I think you know how this is going to roll. We plug in our numbers. Now we get 0.006 moles, which all of that gets consumed in the H3O plus, leaving ourselves with 0.050 and 0.075. Plug those numbers into our Kb problem. We solve for OH minus. We get 1.2 times 10 to the minus fifth. So it's slowly dropping. Now our pH, 14 plus the logarithm of H3O plus. This should say OH minus, my mistake. Should say 14 plus the logarithm of OH minus. And we get 9.08. So our pH continues to drop. All right, at the equivalence point, the moles of acid is equal to the moles of the base, just like the equivalence point in the other problem we did. So at this point, we have 100 milliliters, which is 0.1 liters. So all of my NH3 and all of my H3O plus is consumed, which just leaves NH4 plus. So now when I look at this, all I have is 0.1 molar of NH4 plus. So NH3 is 0 and H3O is 0. So now I change from Kb to Ka, because at this point, the only thing I've got in solution is NH4 plus, and it behaves like a weak acid. Remember, this is NH4 plus is going to donate a proton, and that's the definition of an acid, is something that donates a proton. So when it does so, it forms H3O plus. So now I can calculate what my Ka is. I know what my Kb is. And so for conjugates, Ka times Kb is equal to Kw. So I can get the Ka by dividing Kw by Kb. And I get 5.55 times 10 to the minus 10th. Now I plug those numbers in. I plug in what I've got. I don't know how much I've got now at this point, so that's x. And in my denominator, I have 0.1 minus x. So I'm going to make my simplifying assumption, because at this point, Ka is really small. So I'm pretty confident that I can make a simplifying assumption. When I do, I solve for x, and I get, excuse me, I get 7.45 times 10 to the minus 6, which is definitely a valid assumption. Now that I've solved for H3O plus, I'm just doing a straight pH calculation. So now you can see my pH has dropped significantly by a factor of about 10,000. And all I've done is add 5 more milliliters of acid. So now my pH is down to 5.13. Okay, now I go past my equivalence point, add 5 more milliliters of acid. Total volume is now 105 milliliters. I plug in my numbers, and now I end up with H3O plus that is in excess. Pretty straightforward point or problem at this point to calculate what my H3O plus concentration is. It's 0.001 divided by 0.105. And that number comes out to be 0.00952 molar. Okay, pH is a pretty straightforward calculation because in this case, we definitely have NH4 plus, which acts as a weak acid, but I also have H3O plus, and that's a much stronger acid than the NH4 plus. So I can ignore any contribution to acidity that NH4 plus makes because its Kb is like 10 to the minus, or its Ka is 10 to the minus 10th, whereas H3O plus, that's a 10 billion times stronger. So we can ignore the effects of the NH4 plus. So now when I do this, my pH is the negative logarithm of 0.00952, which is 2.02. So now I'm very acidic at this point. And if we look at our graph, we get our 6 points, A, B, C, D, E, and F. A was our initial pH, 11.28. We added a little bit of acid. We got 9.43. We got to the half equivalence point. It was 9.26. We added a little bit more. We went past the half equivalence point. I got 9.08. And you can see there that in that part of the curve, the pH just isn't dropping very fast. It is dropping, but not very fast. And all of a sudden, I get to the point where the pH just drops like a stone as I pass through the equivalence point. I get 5.12, and then I go on to be 2.02. So this curve looks a lot like the previous problem, but just sort of a mirror image. And in fact, let's look at these mirror images. So when I compare these two situations, on the left, I'm adding 0.2 molar NaOH, a strong base. On the right, I'm adding 0.2 molar HNO3, a strong acid. And the curves are slightly different because the K values are different. One is 4e minus 4, and the other one was less than 2e minus 5. So the curves are going to be shaped subtly different, but essentially the same. We have our 3 points there grouped together. In the middle, we go to a strong inflection point where we get to the equivalence point at point E, and then taper off as we see the effects of getting to the end point of the titration. All right, we're going to stop here. I was hoping to get through all of these situations in one video, but I don't think I can. We'll stop. We'll do another short video and finish up weak acid plus weak base and a few extra points.